lại đến Viện ngày hôm nay. Viện thì có về toán ngoài những cái nhiệm vụ chính của mình là thành lập nhóm chuyên môn nghiên cứu và đào tạo, xây dựng một nhóm chuyên môn về ngành chuyên sâu toán học. Thì cũng có một cái nhiệm vụ tất cả chúng ta đều rất không chỉ niềm vui mà niềm vui, tức là tổ chức hoạt động phòng tập thức như thế này. Đây sẽ là cái bài giảng đầu tiên một chút về giảng phòng tập thức để tiếp cận với những cái vấn đề nóng hổi của khoa học mà chúng ta không nhất thiết phải là có cái chuyên môn sâu gần những vấn đề đó. Có một cái sự ngẫu nhiên, có cái cực kỳ may mắn là cách đây đầu tháng 7 ở bên Thụy Sĩ, nghiên cứu hạt nhân Thụy Sĩ có một cái công bố là trung chuyển vật lý, không chỉ vật lý mà cả khoa học để phát hiện ra một cái hạt cơ bản có thể nó rất giống với hạt Higgs mà đã tìm theo đuổi từ năm qua, 50 năm qua. Ở đây may mắn hơn nữa là ở Việt Nam có giáo sư Darriulat đã làm việc ở Việt Nam từ hơn 10 năm nay. Có con người rất là gần với cả cái sự kiện này. Năm 1984, ông Darriulat đã làm một người phát ngôn viên của một trong hai nhóm nghiên cứu có tham gia vào phát hiện là cái hạt boson V kép và Z. Đến thời gian đó cũng là một sự kiện rất chung về cái thời gian đó. Giáo sư Darriulat hôm nay sẽ nói cho chúng ta về không chỉ về hạt boson Higgs, về cái quan niệm của ông về vật lý đại chúng. Cái bài giảng của ông có tiêu đề là vũ trụ cho chiếc nón. Xin mời Darriulat.
First, let me thank Quang and Prof for inviting me here. I'm very honored, and I hope I will entertain you for 1 hour more, maybe. As you know, just 2 weeks ago, in fact, the announcement was made at CERN that a particle called the Higgs boson had been discovered. And this was received as a big event in the scientific community, because indeed it is, and it received a very gigantic mediatic coverage. So that's what I'm going to report about today. I will first sketch for you the vision of the world which physics has today. It will take 1/3 of my talk. Then I will show you how the Higgs boson fits into this picture. And then I will tell you about what had to be done in order to search for it and finally to discover it, or at least we hope so. So this is what I have on this first slide. Let me just read it. The recent discovery, I'm speaking slowly to start with because I understand that it's difficult for you to understand English, especially my English. So I am trying to maybe repeat sometimes some things. So the recent discovery of the Higgs boson at CERN is an opportunity to review the picture that physicists have of the world today and to position the Higgs boson into such a picture. Now, what is the Higgs boson? Why do we attach so importance to it? Because it's a special particle. It's not like the other particles. It plays a special role, and it is a result of some very elegant ideas, which I will explain, which have to do with the symmetries of the world, and spontaneously broken symmetries and so on. And in particular, it marries two basic ideas in physics, that of a spontaneously broken symmetry, I will explain what it is, and that of the particle masses. That's what I will talk about in the second part of my talk. So the idea of such a particle, relating symmetry breaking with particle masses, was conceived nearly 50 years ago. These are the initials of the names of the people I will tell you who they are later. And its application to the real world was proposed shortly thereafter by Van Dijk and Salam, essentially, and also by Glashow. You see, the fact that there were 6 people, in fact it was 3 independent groups who thought about that was not an accident for the same year, 63, 64. It's because there was an idea which was already present, which was due to Nambu, which was the idea of Goldstone bosons. And then there was a realization of the importance of another idea, which was gauge invariance. And then at that time, it was a bit natural, if you want, that people thought about it. So, in what is known as the standard model of particle physics. And so, that's 50 years ago, and very soon, or at least in the 20 years which followed, this standard model of particle physics, which is very beautiful, very elegant, was verified by observations, by experiments, by many different independent experiments to a very good level of accuracy, between a Fermi and a %. So, we have to believe that this standard model was correct. But this standard model needed a new ingredient, which is this Higgs boson. I will explain why. So the community of physicists felt that it was essential to devote many resources and effort to the search for this particle which should be there. And this is what has happened. So this is something like 30 years ago, that if you want, we became aware of the importance of searching for that particle, because somehow it had to be here, if you want. Well, it's easy to say that now, but that's what we felt. Namely, we were prepared to spend, many physicists were prepared to spend many decades of their life as a scientist, and to convince the governments to spend many $million in order to search for that particle. So the validity of this model was demonstrated about 30 years ago, and the central role of the Higgs boson was immediately recognized. Searching for it became a top priority and triggered gigantic effort from the particle physics community to build the tools that were required for such search, and the tools were what we call a particle collider, which in that case is huge. I will explain to you what it is, but it's a tunnel, a circular tunnel of 27 kilometers in circumference, filled with very expensive material, and the collider and its detectors. Today, these efforts are finally rewarded and open the perspective of a rich harvest of new discoveries. Because the fact that one now found this Higgs boson, I mean, Higgs boson is more a mechanism, if you want, but there must be much more attached to it. There may be many more Higgs bosons, there may be supersymmetry. So we believe that this discovery is the first of a long series which will be accessible to the tools we have, because they are all linked, they are at the same scale, if you want, in energy. So that's a panorama of my talk. I will start by talking about which are the scales in the universe. And I show you a diagram, which you will see again several times, where here I plot them. It's a log diagram. Then between here and here, there is a factor 10 to the 10 order of magnitude, 1 with 10 zeros. So you see from the proton, which is here, to the universe, which is here, there is a factor 10 to the 80. There are about 10 to the 80 protons in the universe. So I plot here the mass in log scale. I chose the solar mass of the sun as a unit. I had to choose one unit. I will change unit later. And here I plot the size of the objects. I chose centimeter. I will again change unit later. So what do you see on this? You see the proton, which is one of the basic elements of atomic nuclei. And you see a dust grain. You see you and I am a bit fatter than you, but at that scale you cannot see it. You see. It's well within the dot. You see the Earth, you see the Sun, and the sun is more or less a very normal star, so all the stars are more or less around here. You see the Milky Way. The Milky Way is the galaxy which hosts the sun, our sun, which contains something like 10 to the 11 stars. And then you see the universe. When I say the universe, I will come back to it. It's not the whole universe, it's a universe which we can see. Because we cannot see farther than some distance in the universe. I will explain why. And we call that the horizon. So when I say the universe, it is a universe which is contained within the horizon. But I will always say the universe without specifying that it is contained within the horizon. So this gives you, there are two lines here. And I'm going to explain what are these two lines. In fact, there is a third line here. These three lines, they are in fact setting limits on the physical world, and I will explain now what they are. So you see on this plot we have 80 orders of magnitude in mass, 60 orders of magnitude in abscissa, in size. So first I will talk about this limit here, and this limit has to do with the quantum world, with quantum physics. So at the beginning of the 20th century, physicists realized that when we were starting to look into matter at the scale of atoms, the ideas which you had of what is a particle and the idea which you had of what is a wave, which were not very clear because it was not clear in which medium these waves were. But anyhow, were wrong, or at least they didn't work. Sometimes an electron was behaving as a wave. We could, for example, make diffraction or interferences. And sometimes the photon, the particle of the light, was behaving as a particle, the photon. For example, when you have photoelectric effect, or Compton scattering. Compton scattering is a scattering of light on the electron of an atom, and it's just like if the light was a particle. So it was realized at that time that these old concepts of particle seen as a material point, or wave seen as deformation of continuous medium, didn't work. We had to change, we had to find a new concept. This new concept today is what we call quantum states. Since I imagine there are mathematicians here in the room, let me open a parenthesis here. One often reads physicists write the equations. I read in a textbook of philosophy of science, physicists write equations, and we philosophers of science, we are here to understand what is behind these equations. It is difficult to write something more stupid than that. It's completely stupid and wrong. It's not true. Physicists are not writing equations. Physicists are doing exactly what's being here. They have a theory, and at some point they realize that the theory doesn't work anymore. So they have to invent new concepts. That's what they do, with which they will describe the world in such a way that they can explain what was not working before. And things don't come with written on their face, I am a force, or I am a vector in the inner space. It's not the way it works. It takes a lot of imagination to think of a force. You know, a force is the same force which prevents the resistance, which acts against gravity when I put things on the table. When I push or when I pull, to make all the same concept of all that is not trivial. And then to understand that this concept can be described as a vector, that you can add them. You can make a scalar product and talk about energy, or a vector product and talk about angular momentum, is highly non-trivial. So what physicists do when they do it hand in hand with mathematicians is to try to find better concepts which describe the world. And they do it hand in hand with mathematicians because the only way to have a simple and rigorous language in this description is mathematics. So when philosophers say that, they just show that they understand nothing to science, which is unfortunately the case of many philosophers of science. So physicists and mathematicians work hand in hand to give a proper status to the new concepts. And today, its quantum states are vectors in a Hilbert space. It was not immediate, you know. For some time there was what we call the wave mechanics of the brain. Then there was the matrix mechanics of Pierre. It took time, it took trial and error before one reached what is today understood as a Copenhagen, if you want, interpretation of the quantum physics. So the way we describe it today is that these quantum states, which are the basic things of which the world is made, are vectors in a Hilbert space. The observable quantities are associated with Hermitian operators. And the eigenvalues, the eigenvectors and eigenvalues of these quantities describe the states in which the quantity in question can be measured precisely as a well-defined value. And since they are vectors, we can add them. So when we have two states, we can define the sum of these two states, even with some coefficients. But they don't have the same eigenvectors, so the result is that we have quantum states in which some of the values which we would like to measure are not uniquely defined, but the result of a measurement will give a spectrum of results. And this is translated in mathematical language by saying that quantities are observable, we say, which are associated with commuting operators, are compatible. They can be, one can measure the corresponding quantities with precision in the same state. But when these commutators are not zero, they are not compatible. This is a case, for example, of time and energy, or position and momentum. Their commutators are not zero. If I am in a state, if an electron is in a state where its position is perfectly defined, uniquely defined, then its momentum is not defined. The same with time and energy. Now, this happens, of course, at atomic scale, at a very small scale. So when not zero means not equal to something very small, in fact. As soon as this commutator, the scale at which we have to evaluate this commutator is very small, it's called the Planck constant. We write it h with a bar. So h bar is a basic scale which tells us at which level we can no longer ignore quantum physics. When we are dealing with quantities which are much larger than h bar, we can happily forget about quantum physics. But when we deal with quantities which are small with respect to that scale, then we can no longer ignore them. It took a long time to abandon the old concepts of wave and particle and accept the new concepts as being the new truth. I put truth in quotes here, because again that's a major difference between mathematics and physics. In mathematics, a theorem which is true today will be eternally true. You may change the hypotheses which you use to demonstrate your theorem, make them broader, and then the theorem will only be true. But if you keep the hypothesis with which the theorem has been demonstrated, the theorem is eternal. In physics, it's completely different. In physics, there is no absolute truth. The truth of today, we must always be prepared to abandon it. If a new truth of tomorrow will give a better description of the world, more complete, simpler, more accurate. So there is no absolute truth in physics. There is a truth of today which hopefully will be replaced tomorrow by a better truth. That's why I put it in quote. So the Heisenberg uncertainty relations are simply the practical expressions of what I just said. It is a non-compatibility of non-commuting observables. And one of their implications is that the product of the mass of an object by its size must exceed the Planck constant, and therefore it sets a limit to the physical world. The product of the mass by the size must be larger than h bar. Now, on this log-log plot, this means that the world must sit on that side of this purple line. So I call this purple line the Heisenberg limit or the Heisenberg separator, and so the world must be above this line. This is the quantum physics which tells us that. Now let's try to understand the other line. Well, first, I will speak about space and time, but as you know, another revolution at the beginning of last century was Einstein's special relativity, according to which the old concepts of space and time had to be replaced by the new concept of space-time. We still are using the same words, space and time, but space and time in special relativity are not the space and time which we used to think about before. In particular, they mix the same way as we have rotation in space, which mix, say, x and y, if we rotate around them, the same way you can have a rotation between space and time. And this rotation is called a Lorentz transformation. Of course, you have to do it with a special metric, -1, 1, 1, but that's a detail. The consequence of that is that the velocity of a massive object cannot exceed the velocity of light, which we call c. And the same way as h bar was setting the limit, the small number h bar, was setting the low limit, if you want, below which we could not ignore quantum effects, c gives you the scale at which you cannot ignore relativistic effects. It's 300,000 kilometers per second, so fortunately, I should not say that. So in most cases of normal life, we don't see relativistic effects because we deal with much smaller velocities. But this gives us a scale where relativistic effects can no longer be ignored. And here again, physicists and mathematicians were uninvolved, and it took a long time to abandon the old concepts and accept the new concepts as being the new truth. Now, I didn't say what happens at large distance. The quantum world is when you look at small distances, when you look at atomic scales, if you want, up below. At large distance, we have gravity. Gravity is negligible at small distance, but it is the only force which subsists at very large distance. You see, electricity, for example, even if it has a long range, it happens that matter is neutral. So the strength, the electricity force coming from an atom in this table, I don't feel it here because there are so many neutral atoms in the table, they screen each other. But the gravity force, they keep adding. So the reason why we weigh is because there is the attraction of all the atoms of the Earth which are pulling on us. So gravity becomes important at large scales. And already Galileo had made a very, very important discovery, but it was not realized for a long time. But gravity has the same effect on all particles. If you have a ball of lead and a ball of wood, say, of the same size, so they have the same resistance against the air, they will fall at the same speed. That's a very major discovery because it shows that gravity has something universal which the other forces don't have. If you have a particle of charge plus and a particle of charge minus, or a particle of charge plus 2, plus 3, plus 4, they will have different electric interaction. But here all particles have the same movement in the gravity field. For a long time it was not realized how important it was. Then came Newton, and Newton described gravity as a force which is a product of a universal constant like mg, the Newton constant, by the product of the two masses which attract each other, divided by the square of their distance, or the energy would be divided by the distance. And it's again Einstein who, he had problems that special relativity did not account well for gravity nor for acceleration. So he wanted to extend special relativity to accelerating frames and to gravity. And he had this idea, because of many things, but that the fact that it is universal allowed him to replace the concept of a force, gravity force or gravity field, by a local acceleration. In some ways the story, if you are in a lift which is falling in free fall, it's a funny metaphor, because I hope you will never be in a lift which is falling in free fall, but if you were in a lift falling in free fall, you feel you are at rest. You don't know whether the lift is falling in free fall or whether you are at rest. For you, the gravity is replaced by the acceleration which is induced, and that's the same for everybody. So that's the basic idea of general relativity, to replace this idea of force and field by a property of space which is induced by the local energy density. I say density, it's wrong. In fact, it's something a bit more complicated than density. It's really the energy momentum tensor. But at the level of this talk, it's enough to say density. So here's a mathematical formulation, heavily relied on relatively recent results at that time of differential geometry, Riemann, Christopher, Levi, Ricci, and so on. And it included a constant lambda, which Einstein calls the cosmological constant. I just talk a little bit about that because it's amusing. You see, at that time, Einstein, nobody, knew that the universe was expanding. He thought, and everybody with him thought, that the universe was static. Now, if the universe is static, why doesn't it collapse on itself? It should fall on itself. So something must prevent it to do that. And since the mathematical formulation of the theory of Einstein was allowing him to put such a constant in the theory, he thought, let me put it in so he will do the job. It will prevent the universe to collapse. And then a few years later, Lemaitre and Hubble and so on, I mean, the idea of an expanding universe was conceived and proved observationally by observation. And then we didn't need something to prevent the universe from falling. It is just the kinetic energy of the expanding universe which compensates the potential energy of the gravitational acceleration. So maybe the universe will have enough kinetic energy to keep expanding. Maybe it will not have enough, it will expand up to a point and then collapse again in a big crunch. But at least we don't need the cosmological constants. And Einstein then was very sorry by saying, as you well know, I imagine, that this was a major mistake in his life to have introduced this cosmological constant rather than thinking of an expanding universe. And then, unfortunately, Einstein died, and after his death, well after his death, at the beginning, I would say at the end of the last century, one realized that, in fact, the universe contains much more energy than what we understand, and we give a name to that, we call it dark energy. And we don't understand it at all. We give it a name, that's all we know how to do. But we know also, we are also able to have an idea of how it acts, which is its action. And it acts exactly as if there were a cosmological constant. So today, astronomers, astrophysicists are led to put back in the theory the cosmological constants for completely different reasons than those of Einstein. But still, I'm sure he would be happy to know that. Maybe he does. So this, what I just talked about, explains the second limit in the universe, which I call the Schwarzschild limit. Because what happens is that when the escape velocity of an object in vacuum reaches the velocity of light, nothing can escape from it, not even light. One has what we call a black hole. You see, if you take the Earth, for example, the escape velocity of the Earth is 11 kilometers per second, so that's not much. If you launch something with higher velocity than that, you will go to space. If it's less than that, you will fall back to Earth. But okay, that's very small compared to the velocity of light. But if the Earth had the same mass and were just 1 millimeter in diameter, that's small, I agree, but if you put the mass of the Earth in 1 millimeter, then the escape velocity would exceed the velocity of light. And so you could not escape the Earth, this tiny little Earth. And this Earth then would be a black hole. For example, the Sun, the radius at which the escape velocity reaches the velocity of light is 3 kilometers. And the Sun, when its Sun will die, it will be a bit larger than that, not much. So it will not become a black hole, it will become something we call a white dwarf. So anyhow, the point is that this argument sets a new limit to the physical world, which is that the ratio now is no longer the product, it's the ratio of the size by the mass must be larger than Newton's constant. In fact, I skip a factor of 2, but never mind. At that scale, we don't care about factors of 2. So this is this line, you see. This is this line. On this line, you find black holes. Cygnus X is a stellar black hole. It's a star which died and became a black hole. Sagittarius A star is a black hole which is in the center of our galaxy, the Milky Way. It is 3 million solar masses, and we know it very well. We know a lot of things about it. And then Cygnus A is a gigantic black hole at the center of another galaxy, but this time it's a black hole which has 10 billion solar masses, billions, not millions. And you also find the universe on this line, but the universe is not a black hole. So why is it here? You see, the visible universe is on this fraction limit, but it is not a black hole, because the universe is not in vacuum. The universe is, if you look behind the universe, there is more of the same, if you want. An observer who would be close to our horizon would see us on his horizon, but he would see a lot of things behind our horizon. How far does it go? Mathematicians will tell you the universe is